السلام عليكم ورحمة الله وبركاته. حياكم الله جميعا. نكمل اليوم دورة هندسة ريمان مع الدكتورة ليانا، عضو هيئة التدريس بجامعة الملك سعود في يومها الثاني. حياها الله. Hello دكتورة ليانا.
Hello, good afternoon.
Good afternoon, doctor.
Thank you. Should I start?
Welcome. Now.
All right, so I'm going to start. Let me. All right. Very well. I'm going to remind you very quickly what you've seen today. So, and then we are going to continue with manifolds and notions and topics related to manifolds. So anyway, first we defined yesterday an n-dimensional manifold, if you remember, an n-dimensional manifold. And this is a topological space which is Hausdorff, second countable, local Euclidean. By local Euclidean, we mean that around every point P, we can find an open neighborhood together with a homeomorphism that takes that open neighborhood of P into an open subset of Rm. We call this pair U and phi a local chart of around P, and such that we can build up an atlas on M, atlas which will give the M the differentiable structure, so the structure of an n-dimensional manifold. So an atlas is simply a collection of local charts, something like that, with any two charts compatible. By this we mean that either that the domains of the charts are disjoint, so either we have something like that, or if the domains are not disjoint, then this transition map from a chart to another, so something like that, with the beta here, which will be defined on the intersection of the phi beta of the intersection of the domains with values here, is smooth. So remember please that this is a subset, an open subset of Rm, and this is also an open subset of Rm. Okay. All right, so something like this, a maximal atlas, right? So we put together all the charts which are compatible, will determine a smooth structure on M. So M will be called a smooth manifold, n-dimensional smooth manifold. Again, the dimension is given by the dimension of the Euclidean space onto which phi takes open sets of M. We saw that this is correctly defined, and so we can indeed talk about the dimension of a manifold. All right, so that was the first thing that we saw, with some examples, most remarkable being the m-dimensional sphere as a subset of Rm+1. This is an m-dimensional manifold, and we saw that we can cover a sphere with two charts. This is one of the one atlas we're talking about. There are other atlases, but what I mean here is that we cannot cover Sm with one single chart, because the domain of a chart is an open set while the sphere is compact. So we need at least two charts. Then we defined a differentiable function at a point. So we say that a function defined between two manifolds is differentiable at some point P of the manifold. So P lives here, and so f of P lives in N, right? I'm going to call it Q, for instance. If for any chart around P on M, so for any chart of M, and for any chart, we call it V psi around Q, so this is a chart in N, this map given by psi composed to F composed to phi inverse, defined like this on phi of Q with values in psi of V, this is a subset of Rm open, and this is an open subset of Rn. So here we have a function which is defined between open sets of Euclidean spaces. So our function is differentiable at f point again in phi of u, which is in Rm. All right. We also took the set of all smooth functions defined on M and real valued, so such that f is smooth. And you saw that this has a structure of real algebra, right? The algebra of smooth functions defined on M with values on R. And then we defined, so once we have a manifold, we take a point P on the manifold, then we can define a tangent vector here at the point P, and the tangent vector is simply a map, defined on this algebra, real algebra of smooth real valued functions defined on M with values in R, which is linear and verify Leibniz rule. Remember, this means that when you apply x, the tangent vector, the x, on a product of functions, that what you get is this Leibniz rule xp of f. Something like that. And then, so this is a tangent vector at the point P to the manifold M. And then we put together all these tangent vectors. So all these maps, and the set containing all these maps is called the so this is tangent vector, right? xp tangent vector at P to the manifold M, and this is the tangent space. The tangent space at the point P to the manifold M, right? Some space like this containing all the tangent vectors there. Very well. Now, we also saw yesterday that this is a vector space being the subspace of the algebraic dual of C of M, of C infinite of M. So this is a vector space, and the dimension of this vector space is the same as the dimension of the manifold M. So we also constructed a basis, a mobile basis, so around the point P. So you take a chart around the point P, something like that, and then we define tangent vectors like that. So dxi is just notation, a little bit weird, just to show that it depends on the chart. So this was by definition the differential of the inverse, which is the inverse of the differential of phi of P applied on ei being the standard vectors of Rm, the basis. E1, Em is the standard basis of Rm, and we define this for every I between 1 and M. So the set containing all these vectors up to the last one, M, phi, and P, this is a basis for this for the tangent space at the point P to the manifold M. So any tangent vector will be a linear combination of this vector. So any tangent vector will be a sum of x, let's say pi, d over dxi phi at P, right? Sum over I. Okay. We also saw yesterday that when you have a function defined from a manifold into another manifold, that this function will induce a pullback. So some phi is f star defined like that, which goes from the real algebra of smooth functions defined on N into smooth functions on M, and f star of some function here, g, whatever. This is g composed to f. The pullback of the function f. All right. Once we have the tangent space at a point of a manifold, we can define the differential of a function defined between manifolds. So suppose that f is a map from a manifold M, n-dimensional manifold M, into an n-dimensional manifold N. Then we can we take a point P here at M, and we can define the differential of f at the point P. This will be a map going from the tangent space at P to M into the tangent space of f of P to N. Right? So remember, say this is M, then you have another manifold N, you have a map here between them, and then a point P, its image through F, and then the differential will go from the tangent space here into the tangent space here. So a tangent vector at P to the manifold M, xp will be taken into a tangent vector at f of P to the manifold N, and the definition was xp composed to f star being the pullback of f. And then we did see yesterday that that's correctly defined. Indeed, this guy here is a tangent vector at the point f of P to the manifold N. And then we also saw that this is a linear, so this is a vector space, remember, this is a vector space. This will be a linear transformation between vector spaces, so characterized by its matrix, and the matrix of the differential of a function f at the point P is in fact the matrix of the local representation of f on this chart at the point f phi of P. And this is simply the Jacobi matrix. So this guy, this one, remember, is a map defined, where did I write it? Is a map defined, it's somewhere here, yeah, it's this one, between Euclidean open subsets or Euclidean spaces. So it's clear what the Jacobi matrix is, matrix of partial derivatives of this function at phi of P. Right, and we saw yesterday some examples of the differentials. All right, of matrices for differentials. Very well. Now, once we defined the tangent space at a point of a manifold to the manifold, the natural thing was to go and define the tangent bundle. Now, the tangent bundle to a manifold. So M is a manifold, m-dimensional manifold. There is an atlas here given by the charts. It's a U alpha phi alpha. Alpha runs over a set of indices here. And then this guy was simply a disjoint union of all the tangent spaces at any point to the manifold M. Right, so here you will have all tangent vectors. Fix it at the point P to show this joint. And then there is a natural projection of the tangent bundle over M, which takes, you see, an element here, it's something of the form xp, it's a tangent vector at P, or pxp, if you want, right? Something like this. So this goes into P via the projection. We also saw that pi inverse of the pre-image of the point P is the same thing as is in fact TPM, and we call it the fiber about P. Once we defined this, we talked a little bit about the fact that this tangent bundle has a structure of smooth manifold. So it has it has a topology, a well-defined topology, and then it's Hausdorff, it's second countable, and we did define an atlas here. So say this is an atlas on M, then an atlas on this tangent bundle is given by something like this. So the domains of the chart are pi inverse of U alpha, and the homeomorphisms are, we denoted them by tau alpha. Okay, every chart here on M will induce a chart on the bundle. Well, we saw that pi inverse of U alpha is simply the set containing all tangent vectors at the point P, right, where P runs over all the points. P can be any point of U alpha, while tau alpha, the homeomorphism, was defined like that, into phi alpha of U alpha times Rm. So this being a subset of Rm, this Cartesian product will be a subset of R to M, and the definition was that every point, every tangent vector, so something like this, will be taken into, so we take its image to phi alpha, this lies here, and the differential of phi alpha at P computed at the vector xp, right? We did see that this is indeed, this will determine a smooth structure. So this Tm will turn into a smooth manifold itself, smooth manifold with dimension 2m, so 2m dimensional, twice the dimension of the manifold M. Now, this is pretty much what we've seen today with some examples, and because we did talk about the tangent bundle, and I didn't give any example yesterday, so let me take two very simple examples today for the tangent bundle before moving on. So let's look, for instance, at the tangent bundle of the Euclidean space Rn. Okay, let's see what it is. So we know that Rn is a smooth manifold, n-dimensional. In every Euclidean space is a smooth manifold. The dimension is n. We can cover it with one single chart. Is the domain is the space Rn itself, and the homeomorphism is the identity. And then, so let's see what is this. So by definition, remember, this is this joint union of the spaces tangent at any point of the manifold, so Rn, to the space Rn. I'm going to put here P just to show that this is the space Rn at P there. Okay, so this will be in fact what? This will be the union, or this joint union of, well, how can I identify this space tangent at P to Rn? Is Rn with the origin at P, right? It's the origin there. But now, what is Rn? The tangent bundle of Rn is R2L Euclidean space. Now, an example a little bit less obvious. I mean, it's still not very complicated. Let's see what is the tangent bundle to S1, right? So S1 is a circle, right? One-dimensional sphere. This means a circle. So taking like this with radius 1. Remember that we saw yesterday that every sphere is a Sn is an n-dimensional manifold. So this S1 manifold. All right, let's see what is the tangent bundle to this. So again, by definition, this is what? This will contain all tangent vectors together with their origin. So P runs over S1, and XP is a vector which is tangent at the point P to S1. Okay, now imagine that, so P so it's a point on the circle here, right? It's something like this. Remember, when I'm saying S1, we say the radius is 1, right? So it's a unit circle. So every point here, right, if you are familiar a little bit like this, you can see that if you denote this angle by a theta, then this point here, point P, will have coordinates cosine of theta and sine of theta, right? You know this. So the point P will be like this. Now so P is in S1, and we'll have these coordinates. Now what is XP? It's a vector which is tangent at the point P to S1. So it's perpendicular. So tangent means perpendicular on the radius here, right? From the very simple properties of the circle. So we can very easily see that in fact the direction of this vector will be given by the derivatives here of the or you just go orthogonally there. So if we take this vector, so the tangent vector here with length 1. The direction of this vector is given by minus sine of theta and cosine of theta. Take, for instance, derivatives of those components to give the direction, and then so a tangent vector will have this direction. It doesn't necessarily have length 1, right? So let's say the length is some lambda. So the components of the tangent vector will be negative lambda sine of theta. I'm just giving a length to this vector, right? Something like this. So this is what a tangent vector at the point P to the circle looks like. So now we can identify, you see, we can identify the tangent bundle to the circle, and S1, so the circle times R, something like this, through the following map. I'm going to call it H, for instance. So I'm taking a point here in, right? So in the tangent, so a point like this, P, XP. So this point is in fact what? So it's H instead of P. Well, P is the point cosine of theta, sine of theta, right? And then xp is minus lambda sine of theta and lambda cosine of theta, right? So what are the, what are the things that characterize that pxp, the tangent vector? Theta, the angle, right? So cosine of theta and sine of theta together, which will give a point on the sphere, and lambda, which is a real number. So we can identify this by, okay, so the h of this tangent vector will be cosine of theta, sine of theta, and lambda, right? This guy here is our point P. So this is in fact what? This is in fact, right, P lambda. So, which shows that the tangent band, so this is in S1 on the circle, and this is in R, right? So in fact, the tangent band of the circle will be the same thing as S1 times R, right? So something like this. Right, so this is how we can determine tangent bundles to manifolds. Okay, these are simple examples of tangent bundles. We say that the tangent bundle of S1 is trivial because it's the manifolds times R, right? It's something like that. Tm, the tangent bundle, is of form m times R. Call it trivial. All right. Do you have any question before I start talking about submanifolds? Any question? Questions? All right. Then let me go here. All right. Okay. So we are going to see what a submanifold of a manifold is. And for this, we are going to start by defining the rank of a map between two manifolds. Well, as always, as before, right, when we were talking about differentiability, or we were going to go through a local representation of the functions. So when our function is defined between Euclidean spaces, we know what the rank of a transformation of a map like this is. It's simply the rank of its matrix, right? So the rank of the Jacobi matrix. So we are going to define. So if f is a function defined between two manifolds, then the rank of the function is defined to be the rank of the local representation of f, right, at the corresponding point. So let me see if I can maybe write here. Okay, well, whatever. So, sorry. All right, so I'm going to take anyway examples. Now I remind you here what is the local representation. You've just seen it on a quick revision from yesterday. So remember, the rank of a function at a point is the rank of its local representation in some charts. Now it can be seen that this is independent. This is independent on the choice of the local chart, and this simply comes. I wrote it here. You see, the local representation of f in two charts, phi1 and psi1, can be seen as a product between a diffeomorphism, then the local representation of f in the original chart, phi psi, times another diffeomorphism. Now, but when we apply the differential and the chain rule for the differential, remember chain rule acts on differential of functions, then the differentials of for the diffeomorphisms will be automorphism of Rn, right? So the rank doesn't change. They will not change the rank. You will have some square matrices there which are non-singular. So the rank of the differential of f in the charts phi1 psi1 will be the same as the rank of the differential in the chart phi psi. So this just to say that when we define the rank of a function at a point through the rank of its local representation, then the definition is correct, right? If we change the local chart, that the rank doesn't change, remains the same. Now it's clear that the rank of f being the rank of f5 psi, the local representation, which is a map from an open set of Rm into an open set of Rn, this rank cannot be greater than the minimum between m and n, between the dimension of the two manifolds. So for the particular cases in which the rank is either m or n, depending which one is smaller, these maps between manifolds have names that are important in mathematics. We call them immersion or respectively submersion. So so you see, let's suppose that F is a smooth map between manifolds M and N with dimensions M and N. Let's suppose that the dimension of the domain M is less than or equal to the dimension of the codomain of N. Then if the rank of F at the point X is exactly M, so the maximum possible, right? Again, the maximum possible is the minimum between M and N. So in this case, M, then we say that F is an immersion at the point X. And again, like always, if F is an immersion at any point of the manifold, then it's said to be shortly an immersion. Now, if on the other hand, on the second case here, the dimension of M of the domain is greater than or equal to the dimension of the codomain N, and the rank of F at X is M, so again the maximum possible, but which now in this case is the dimension of the codomain, then we say that F is a submersion at the point X, and again submersion on the manifold if it's a submersion at any point X. And now there are some equivalent statements here which are pretty they come easily from linear algebra. So again, suppose that F is a smooth map, okay, if M is less than or equal to N, and the rank, so let's say X is a point here of M, if the rank of F at X is M, then F is called an immersion at X. And if M is given to be greater than or equal to N, and the rank of F at X is N, then F is called a submersion at the point X. Now, you see, it will be an immersion at the point X. This is equivalent with the fact that, with the fact that the differential at F of F at X, which remember is defined between the, okay, that's not P, it's X, something like that, F of X at N, this is defined between the corresponding tangent spaces, so if and only if this is injective, one-to-one. See, this comes from the fact that, so immersion at X means what? Means that the rank of F is M. So remember that the dimension of this space is M as the dimension of the manifold to which it's tangent, and this is N here. Now, if the rank, you know what the rank of so this is the same. This map here, right? This is a linear map between vector spaces. You know that the sum between the rank and the nullity is the dimension of the space. So M, if the rank is N, then the nullity of this map will be 0. What's the nullity? It's the dimension of the kernel. So this means that the dimension of the kernel of this map is 0, but the kernel is a subspace here in the tangent space at X. To M, what is the subspace of dimension 0? This means that the kernel of the differential at X only contains the vector 0, but this means precisely that the differential is injective. And F will be submersion at the point X, if and only if, so you see we characterize this submersion via the differential of the function, if and only if the differential, right, again defined from Txm into Tf of xn, is a surjective map onto, right? So submersion means that the rank is n, but the rank is n means that the dimension of the range is n. So the range of the differential has a dimension n, but the range is a subspace here. So we have a subspace of this vector space, n-dimensional. So this is n-dimensional. The range is n-dimensional, which means that the range of the differential is a subspace of T of the same dimension as the space itself, so it must be the same. So the range of the differential is the whole space, right? But this means precisely that the differential is surjective, right? So these are simple things related to immersion and submersion. So going back to this presentation. Very well. So this is what we have here. And now I'm going to skip a little bit here, and I'm going to try today to give you a little bit more computational examples, so we try to understand better what is this and to see that there is geometry on all this very heavy, if you want, theoretic part. So if f is if an emotion at this C infinite from m and n means the set smooth functions defined on the manifold m with values on the manifold n. Suppose that this is an emotion at some point, then there is a local representation. So we can write f in local charts. We can find some charts about x on m and about f of x on n, such that when we write that local representation of f around the point x, the function has exactly this form. You see, a very nice form. So the rank is m, right? So when you write, if you want the matrix here, right, then what you get is identity, right? The identity matrix of size m, right, of dimension m, and 0 at the bottom, right? Also, when you have a submersion at the point x, then you can find the local representation for this function, which looks like this. You see, m is greater than n, so you simply cut the last coordinate. So again, when you write down the matrix, you will get some identity matrix there, right? So very simple ways to see the immersions and the submersions, to understand them. All right, now we are ready to go and see what is the submanifold. So I'm going to go directly with this definition. So you see, suppose that you have, maybe this deserves that I explain it on a white paper. So, all right, something like that. So suppose that M is a manifold, an M-dimensional manifold. So again, this means that we already have an atlas on M, which is a collection of charts. So say U alpha, phi alpha. Okay, and suppose that N is a subset of M. Okay, so say this is M. Say this is M, and then we get a subset of M here. Okay, now we say that N is a submanifold. So submanifold, so n-dimensional submanifold of the manifold M, if something like this happens. So every time you take a point x here on N, on the manifold, you can find a local chart around the point x. It's a local chart from your original atlas on M. So because x is in N, it will be on M, so you can always find the chart around the point. So say a chart of the form, this is the domain U alpha, the domain of the chart, together with the homeomorphism phi alpha. Now, from the fact that M is a manifold, this homeomorphism will go into an open sub. So phi alpha of phi x, let me call it phi x to show that it's related to the point x there. So phi x of ux will be a subset of Rm, right? Because we have an n-dimensional manifold. An open subset of Rn, and right, so nothing new here, but in order for N to be a submanifold of M, then we need to have something like this. We need to have that the intersection, the image of the intersection between ux and N. So this part here, you see, this image must be in fact the intersection between phi x of ux, so the image of the original image of the open set of the domain of the chart, together. So the intersection with Rn times 0, 0, 0, 0, n minus n times. So we want n minus n on the last components, right? This looks a little bit like emotion, like an emotion. So of course, n here will be smaller than m, right? So because it's a submanifold, we won't have submanifolds with greater dimension than the space where we are. This will be R arrow minus N. And then this is intersection between phi f of u and R 0. All right, so something like this. So this is, as I said, this is an n-dimensional submanifold if for every x n there exists ux phi x, a chart on M such that this happens. Okay, now it can be seen that this is N is a topological space itself, then it's Hausdorff, then it has a countable basis, and then it will be a smooth manifold with the atlas, the one induced from M. So you simply take all the intersections between U alpha and N, U alpha being, you know, the domains. I mean, you take every chart on M and you intersect it with N, and then for the to U alpha, something like that. So this will be an atlas on N. So N will be an n-dimensional manifold itself, right? Now, all right, now we have something like that, and then we would like to find, you know, a nicer way to find submanifolds of manifolds, so to show that subsets are submanifolds without, you know, going to these charts all the time. And there is a very nice theorem which I will give in a second. So let me, before this, define a regular point and a critical point for a function. So this is what you've seen. Okay, so suppose that you have a smooth map between two manifolds M and then we take a point on the manifold M. If the rank is exactly the minimum between M and N, so remember the rank is always less than or equal to the minimum. If the rank is exactly the minimum between M and N, which means what? Which means that F is either an immersion if M is less than or equal to N, or a submersion if M is greater than or equal to N, with what we've seen before. So if the rank is exactly the minimum, maximum possible between for a map defined like this, then X is called the regular point of the function. Otherwise, X is called the critical point. So what is a critical point of a function? Is a point at which the rank is strictly less than the maximum possible rank, which is minimum between M and N. Okay, so it will be regular if the function is regular. So X will be a regular point if F is either an immersion or a submersion, and otherwise this will be a critical point. Now, suppose that you take a value of y, right, so on the codomain of the function, and you find the pre-image, so f inverse of y. If this set contains only regular points, then this is called the regular value for the function. Otherwise, it's called a critical value. And now we have this very nice theorem that I call here pre-image theorem, which gives us a way to show that a subset is a submanifold of a manifold. And this theorem, I'm going to, let me write it, go on on this white page. Okay, so the theorem says the following, says that if F is a smooth map between manifolds, so smooth, differentiable, right? Smooth maps between manifolds. Suppose that M is greater than or equal to N, right? And suppose that Y, which is here, is a regular value of the function F. So remember again that a regular value is a Y for which, so this means that F inverse of Y, right, which is the set of all x's of M for which f of x is equal to y. So all these points x going into y are, so this only contains regular points. of f, that is the rank of f at the point x, where it's minimum between m and n. Now here this will be n. So this simply means that f is a surjection at the point at that point. Well, so if this is a regular theorem, if this is a regular value of f, then this f inverse of y is either empty or m minus n dimensional submanifold of the manifold M. So we can build up submanifolds of M if we can see them as the pre-image of a regular value of this function, right? And I would like to take some examples here, you know, with all this rank, and it's very computational, so let's try to do this together a little bit. I'm going to come back maybe to this theorem with the, all right? So let's look for it. Okay, so let's look first here. Oh, I skipped. All right, so let me go first to the second one. I'm going to come back to the first one because I remember, this is why I put it here, because I remember that yesterday I talked about local diffeomorphisms and global diffeomorphisms, so I want you to understand what it is. I'm getting back to question number 1. So first, let's look at this question 2. Let's do this some computations together, so you understand how we calculate it. So I'm taking the following function. So I'm taking f from r squared to r, given by f of x and y equals to 3xy minus x cubed minus y cubed. All right, and I would like to find the critical points. I think this is what we were asking for, right? Here. So we want to find the critical points of this map, right? So critical points. The set of all critical points is called the critical set of the function f. All right, so I'm going to write like this. C of f is what we denote by the critical set of f, and this is the set of all critical points of our function f. Okay, so a point xy will be critical if and only if, that's the definition, the rank of f at the point xy is strictly less than the minimum between the dimension of the domain, which is 2, and the dimension of the codomain, which is 1. Now this minimum is 1, so strictly less means that the rank must be 0. So this xy, right, the point with coordinates xy is critical for our map f if the rank of f at the point is 0. Now, what is the rank of f? The rank of f at some point is the rank of the differential, which is the rank of the Jacobi matrix of f at the point xy, which is the rank, right, of, so the derivative with respect to right? 3x squared, sorry. So with respect to x, 3y minus 3x squared. With respect to y, 3x minus 3y squared, correct? So this rank must be 0. When such a rank is 0, when the rank of this matrix is 0, when both entries of the matrix are 0, right? Which means 3y minus 3x squared equals 0, 3x minus 3y squared equals 0. So this means x equals y squared, or y equals x squared, and x equals y squared. Okay, if we replace it, we take this y, we'll put it here. So we have x equals x to the power 4, right? Or x times x cubed minus 1 equals 0. So you have x equals 0, you have x equals 1. If x is 0, then y is, so y is what is, not y is x squared, so 0, and here y equals 1, right? So what are the critical points? What are the critical points of the function? The first one is 0, 0, and the second one is 1 and 1, okay? So these 2 points are the critical points of the function. Every other point with coordinates x, y will be a regular point for the function. Now, what are the critical values? Critical values means the images of the critical points. So critical values of f are f of 0, 0 and f of 1, 1, right? So if we replace in the expression of f, where is f? This one. So f of 0, 0, that's 0. And f of 1, 1, that's 3 minus, that's 1, right? So 0 and 1 are the only critical values of our function f, which means that every number, I'm not going to call it y, I'm going to call it z, every z which is not 0 or 1 is a regular value of f. I'm talking about regular values because I want to go and apply this theorem, take some examples for this theorem, saying that f inverse of a regular value of the function is a submanifold, so manifold itself, all right? So that's one example here on how we compute critical values. Also, let me take maybe see what else I put here. So that was the second one. Okay, let's look at 2 because it's pretty easy, so you have more than just one example. So we take a function, so f. Now this is defined on r squared with values on r squared given by f of x and y equals x squared plus y squared and x plus y. And again, we want to find the, let's find the critical points, critical values of the function, all right? So a point will be critical for f if and only if what? The rank, again, by the definition of the function f at this point is strictly less than the minimum between 2 and 2. Now, the minimum between 2 and 2 is 2. So this means that the rank is an integer positive number. The rank is 0 or 1. Okay. Now, what is the rank of a function? It's the rank of the Jacobi matrix. So if we write down the Jacobi matrix for f, right, what we get is, so this is our function, the derivative with respect to x, with respect to y, with respect to x, with respect to y. So it's something like this. You see, the rank of this matrix is never 0 because you have non-zero entries. This is a non-zero entry, for instance. So the rank, so xy will be critical for this particular example, if and only if the rank of f is 1. When is the rank of f1? This is equivalent with the determinant, right, from the classical theory. The determinant of this Jacobi matrix equals 0. But this is what is the determinant. The determinant is 2x minus 2y, which is the same as saying x equals y. So the pair xy is a critical point of this function when the 2 coordinates of the point are equal. So the critical set of the function contains all pairs of the form xx, right, where x is any real number, right? So it's a whole line, right? It's a whole y equals x. This is the equation. It's a whole line of critical points, right? This is the first bisector of the system of coordinates. Okay. Now, what will be the critical values? So I want to compute. So for the critical values, I need to see values of f. I need to see the value of f on a critical point. So on a point of the form xx, right? So where is the function? Okay, it's x squared plus y squared, so which means x squared plus x squared, 2x squared, and then it's an x plus y, which means 2x. So the critical values, verify this equation. So the first, I'm going to call it a capital X. This is 2x squared, and the capital Y is 2x, right? So every point having this kind of coordinates will be a critical value. The values are not real numbers here, right? Because the function is defined onto r squared. So what is this? If you take x here, x is y over 2, right? So you x small x. So you plug it here. So the capital X is 2 times y squared over 2, and this will be a parabola, right? A parabola. So we have a whole parabola of critical values, and any point which is off this parabola, right, is a critical value for the function. Okay, so I hope it gets a little bit clearer now. Let's look at why I cannot. All right, yes. So let's look at question 4. Sorry. 3 just so let's prove that this x cubed plus y cubed plus z cubed equals 1 is a manifold of dimension 2. Now we know already, right, about this x squared plus y squared plus z squared equals 1. This is a sphere. This is the sphere in r squared yes, it's the two-dimensional sphere. So but I would like to go and see apply this theorem, right? So we were talking about, so I'm going to back to here. All right. Okay. So this is S2, right? So this is S2, contains all triples x, y, z, for which x squared plus y squared plus z squared is equal to 1. This is a two-dimensional sphere, okay? Now, I would like to show that this is a two-dimensional manifold. Okay, so two-dimensional manifold. We know that it is two-dimensional manifold, right? It's a sphere. But let's apply this theorem. You see that this very, very nice result, saying that when you have a function defined on a space which is on a manifold which is of higher dimension than the codomain, then if inverse of a regular value, if it's either empty or it's an n minus n submanifold, n minus n dimensional submanifold of M. So let's try to apply this theorem here. Let's go and define a function. So I'm going to define f on R cube with values in R. So you see that already the dimension of the domain is 3, which is greater than the dimension of the codomain. And we take the function to be f of x, y, and z to be x squared plus y squared plus z squared. Okay, something like that. Well, we would like to find the critical value. We'd like to find the regular value. So for this, let's start by computing the critical points of f. So the critical points of f are what? All triples x, y, z, for which the rank of the function f at x, y, z is strictly less than the minimum between the dimension of the domain, which is 3, and dimension of the codomain, which is 1. So strictly less, so minimum between these two is 1. So this means that we'll have all the triples here for which the rank at the point is equal to 0, right? Strictly less than 1. But what's the rank of f at a random point x, y, z? This is the rank of the Jacobi matrix. So the derivative with respect to x, the derivative with respect to y, the derivative with respect to z. So this must be 0, but this is equivalent with the fact that all entries are 0. Everything is 0, right? That's the only possibility. X, y, z are 0. So the only critical point of the function is the 0, 0, 0, the origin of the system of coordinates. That's the only critical point. What will be the critical values? F, the values that f takes on the critical points. So the critical values of f, well, there is only one, right? Because we only have a critical point. So it's only one critical value. It's f of 0, 0, 0, f of 0, 0, 0, which replacing here is 0. So the only critical value of the function is the number 0, which means that every number which is not 0, right, every element of R, every real number which is not 0, is a regular value of f. So in particular, y, well, okay, I'm not going to call it y again, I'm going to call it whatever, k equals 1 is a regular value is a regular value for our function f. But regular value means what? That its inverse, where is its pre-image, if this is a regular value of the function, its pre-image is either empty or an m-n submanifold, dimensional submanifold of M, so of the domain. So this means that f inverse of 1 is either empty, the empty set, or submanifold of R3 of dimension 3 minus 1, 3 minus 1, m minus n, right? So, or a two-dimensional submanifold of the domain, which is R3. Now, what is the pre-image of 1? This is given by all the points, all the triples, for which f of x, y, z is equal to 1, right? This is how we define the pre-image. But this, if you look at the expression of the function, means x squared plus y squared plus z squared. So this contains all triples x, y, z, for which x squared plus y squared plus z squared is equal to 1. This is precisely our sphere, right? This is not empty. It's enough to, for instance, the point with coordinates 1, 0, 0 belongs to this one. So it's not empty, right? This is not empty, which means that it's a two-dimensional submanifold of R cube. So the two-dimensional sphere, right, is a two-dimensional submanifold of R cube, right? It's a nice way to find submanifolds. You see, submanifolds are manifolds themselves. So we can draw the conclusion that this S2 is a manifold of dimension 2, right? 3 minus 1. Okay. Now, same for question 5. We will have the Jacobi matrix. This will be a 2 by 2 matrix. So this is about. We have some more examples here. So I would like to take. The first one here with this immersion thing, and also I would like to look at this question number 1. Okay. Because again, we did talk a little bit. We had a few words yesterday about local and global diffeomorphisms, but we didn't take any examples. So let me take this one before going and talking about that immersion. So just a second, cosine of y. I'm writing it on a paper. I don't. All right. So here we are. Okay. So we want to show that. So we have the following map. Let's say f defined on r squared onto r squared minus, we take the origin out, and then f of x and y equals exponential of x cosine of y exponential of x sine of y. So this will be f will be a local diffeomorphism, but not global diffeomorphism. All right. So a global diffeomorphism, if you remember from yesterday, means a function which is bijective, smooth, and the inverse is smooth. Okay. Now it's clear that our function is not a global diffeomorphism because it's not bijective, right? It's not one-to-one because of these trigonometric functions here, right? These are periodic functions, so it's clear that this function is not injective, so it's not a global diffeomorphism. Now, local diffeomorphism means that about every point, so local diffeomorphism at some point xy, I did define it yesterday, but I'm going to just remind you. These are notions which appear a lot in these manifolds topics. If it's a local diffeomorphism, if locally is a diffeomorphism, so this means that we can find a neighborhood. So you open about open set containing this point, such that the restriction of F to this set, defined such that this is onto, is a diffeomorphism. So locally is a diffeomorphism. Now this comes down with the fact that the differential of F is an isomorphism at xy, is an isomorphism of vector spaces. Remember, this goes from the tangent space here, but which can be identified by r squared, to the tangent space here, which again can be identified with r squared. You see, tangent space at the Euclidean, imagine r squared, which is the plane, right, the board I'm writing for. So if you take a point here, a tangent vector, right, to r squared, to the board is any vector in r squared. So you identify, you just fix the point here. All right, so this is an isomorphism. This is equivalent with saying that the matrix of the differential is non-singular. Right? But what's the matrix of the differential? Is the Jacobi matrix, right? So non-singular. So what is the Jacobi matrix for this thing? So again, partial derivative, I'm looking at the function. Partial derivative with respect to x, that's exponential of x cosine of y. Partial derivative with respect to y. Partial derivative with respect to x, partial derivative with respect to y. All right, so this must be non-singular. So when we compute the determinant of this matrix, what we get is exponential of 2x cosine squared of y minus plus exponential of 2x sine squared of y. We take exponential of 2x as a factor times cosine squared plus sine squared, which is 1. So you see, this is the determinant of the matrix, which is never 0. So indeed, our Jacobi matrix is non-singular. So the differential of f at any point is an isomorphism. So this is a local diffeomorphism at any point, but it's not a global one because it's not a one-to-one map. It's not bijective though. Okay? Any question here? Any question? Okay, then let me take one more example here, which is I would like to also take something with immersions and okay, so let me take the first one, okay, to see how we compute the rank also for some maps. Okay, so let's be just good. I have something. Okay, there is a no on the chart. All right, so this means that no questions, I suppose. All right. Very well. So the question says the following, says that M is a smooth manifold, and then we take a smooth submanifold, so with dimension n, smooth, they are all smooth on this lecture, right? So manifold. Okay, so prove that the inclusion of n into M, so this simply is given by I of x equals x, right, for every x of n, is an immersion. Right, so we can calculate, we have an example where we calculate rank, the ranks of an M. All right, so let's go and see this for an arbitrary manifold. You see, this inclusion is an application between manifolds. So we need to come down, when you compute the rank of I, we need to come down to local representations, right? So what I'm going to write here so I remember it. So I will be an immersion if and only if I is an immersion with any point x of n. Okay, so we are going to show that I is an immersion of any point x of n, and this is equivalent with the fact that the rank of the map I at any point x of n, right, of n, is immersion, means the minimum, well, means the dimension, so this is n, the dimension of the domain n, which obviously is less than or equal to m because of the submanifold. So this means immersion at the point A. Now, what is the rank? So again, let me write it, this I again here. So we see it goes from n into M. So what is these are manifolds, right? So suppose that on M we have an atlas which has some charts, U alpha, phi alpha. And then the corresponding atlas on N, remember, you simply take the intersection of the charts of N with N, and then you restrict this phi alpha to this intersection, right? Again, alpha over A. So I'm taking a point X here. This will be the inclusion, which is again X. So if you take here a chart about this point and the chart about this point, if this chart is of the form U alpha, phi alpha, right? Then so say this is A, this is M, seen as manifolds, right? N, M, something like that. Well, N is a submanifold, so it's practically a subset of M. It's just for us to see it a little bit better. So if this is X, and this is the same X, right, which I of X, so you take a chart here and the chart here. If this chart is of the form U, I'm going to drop the indices, U alpha, then this chart will be of the form the intersection of U and N, the restriction of phi to the intersection between U and N. So what will be the rank? What is the rank of the application N at the point? It's the rank of the local representation of I, in the charts phi, the restriction together with phi at the point phi X. Well, the restriction here, but it's the same thing. So this is the rank of the map phi composite I, the inclusion, composite the restriction of phi inverse, okay? And this will be defined, so this guy here, this function is defined from, so I'm going to write it again. So let me call it G so I can, okay, something like that, a little bit shortly. So this will be defined on the restriction to the intersection of U and N with values in phi of U. Now this is, remember, an open subset of Rm, because this is a chart in M, while this one, from the definition of the submanifold that we've seen at the beginning, components are zero. So, okay, so this is how we define the submanifold. So let's see what we want the rank of this map. Well, at some point here, phi of X, whatever. So I'm going to call it Z, this phi of X, so it's a little bit shorter. So what is G? I'm simply computing the expression of this function. So this is phi times I times the restriction here, inverse, applied on Z1, Zn. Now, what is this part here, you see? Well, you take phi of U and the last component will turn into 0, 0, 0. So this will be phi times I times phi inverse applied on the vector Z1, Z2 up to Zn, and this is n is the dimension of the submanifold, and the last components are 0 here, all right? So this will be equal to phi times I applied on this phi inverse, right? Phi inverse of Z1 up to Zn and 0, 0, and minus n times. So I of phi will be phi, right? Because I of X is X. This is the inclusion. So you will get a phi of phi inverse of this Z1, Zn, 0, 0, 0, which means Z1, Zn, and the other m minus n components are 0. See, this is the local representation of the inclusion. So the local representation of the application of the inclusion map of I of X equal X from the submanifold N to the submanifold N to the submanifold M has this local representation, right? So that application has this local representation. Now, in order to show that this is an immersion, remember, we want to calculate the rank. So the rank of G at a point Z is the rank of the Jacobi matrix of this function, right? Of the Jacobi matrix at so now we go with the partial derivative with respect to Z1 is 1. So 0. So here you have n columns, right? Then you will have 0, and with respect to z2, imagine there is a z2 here, right? Partial derivative with respect to z1 is 1, z2 with respect to z2, with z1 is 0, with z2 is 1, 0, and then you have other zeros coming from these ones, right? And then you go until n, so this is 0, 0, I'm here at this function, and then you have some zeros here, and then you have the rows, a lot of rows of 0, 0, 0, 0, right? Something like that, given by the partial derivative of the function 0. So this guy here, right, this block, this matrix block is the identity matrix of order n. So and everything else is 0, so what is the rank? The rank is indeed n, right? So the rank is n, which means that the rank of the inclusion is n, so it's indeed the dimension of the domain. So this is an immersion at any point. The inclusion is an immersion at any point. Understand? Is it clear? All right, so hopefully yes. Let's see what else is here. Yeah, so pretty much the same way to do this. We have like 8 minutes before the break. So I'm going to not start a new section, right? I'm going to simply take an extra example. Let's say example, let's look at example 5, right? Because we have here, you know, two restrictions there on S, okay? So I'm going to take example 5 before the break. Break, it's still at 6:20, right? Okay, I suppose yes. So we want to show that the set S, so let me see this chart. No, yes, okay, yes. All right, so we take the following set, a subset of R cube, defined like that. So all triples, X, Y, and Z, such that X cube plus Y cube plus Z cube is equal to 1, and X plus Y plus Z, this is cube, and X plus Y plus Z is equal to 0. So you see, you have the intersection between some surface, this X cube plus Y cube plus Z cube equals 1, and in the plane, X plus Y plus Z equals 0. And we would like to show that S is a one-dimensional, I think it's one-dimensional. Let me check the question here. Yes, a one-dimensional submanifold of R's. So, okay, is a one-dimensional submanifold of R cube. So we are going to use again that theorem that we saw. So we are going to define a function on R cube with values in R squared this time. I'm going to define it like this: f of x, y, z equals to, so I'm taking the first component to be x cube plus y cube plus z cube, and the second component to be x plus y plus z, okay? And now it's pretty clear that our S, right, the set we are talking about, is f inverse of 1 and 0. I think this is clear. Now, if we can show that this 1, 0, so if we prove that 1, 0 is a regular value of f, then the conclusion follows, because regular value means that the set S is either S is empty, which is not. It's very simple to give a point there, or S is a submanifold of R cube with dimension the dimension of the domain, which is 3, minus dimension of the codomain, which is 2, so dimension 1. So in fact, we just need to show that this 1, 0 is a regular value. So we do the same thing. We go and calculate the critical points, then the critical values, and everything else is a regular value. So we want the critical points of the function. So a triple xyz is a critical point. If and only if, by the definition, the rank of f at the point xyz is strictly less than the minimum between the dimension of the domain and codomain. Now, this minimum is 2. So this says that the rank of f at the point xyz strictly less than 2 is 0 or 1. Okay, so let's go and calculate the rank of this map, of this point. Of this map at the point x, y, z. So this is what? This is the rank of the Jacobi matrix at the point x, y, z. So partial derivatives. In first function, the first part, which is this. So with respect to x, with respect to y, with respect to z. And then second, with respect to x, with respect to y, with respect to z. So it's something like this. So we want this rank. We want this rank to be 0 or 1. Now, it cannot be 0 because you have non-zero entries. So this rank must be 1. And this is equivalent to what? All determinants of order 2 are 0, right? The rank of a matrix. So this says something like this. This determinant equals to this one, equals to this one, and equals 0. So the first determinant is x squared minus y squared. So x squared must be equal to y squared, and this must be equal to z squared. Okay, so something like this. So x is plus minus y is plus minus z, right? And x is y is, so x is plus minus y, plus minus z, and y is plus minus z as well, right? So these are the critical points. Now, so what are the values of f at a critical point? So we'll have something like this: x plus minus x plus minus x, right? It's not very correct what I'm writing because it's plus. It could be plus minus anyway, something like this. So what are the critical values? Critical. I mean, it's not that we need to write it a little bit better than this, but like we are speeding. Critical values of f. So you will have what? F of xxx, right? So this is what? This is 3x cubed and 3x, something like that. Then f of x minus x and x. So you will have some x cubed and x, and so on, right? This kind of values we'll have there. So of critical value. So, but when you look at what we want, 1, 0, you see, is neither of the form 3x cubed and 3x, nor of the form x cubed times x. So this 1, 0, right, is a regular value. It doesn't have the shape of a critical value, right? So 1, 0 is a regular value of x, of f. So is a regular value for f. And the conclusion follows, right? It's pre-image, so S is a submanifold of a one-dimensional submanifold of R cube. Okay, so I think we are going to take a break right now. Any question, please?
Yes,
Any
Doctor.
question? Yes. All right.
أي سؤال? Any question? I wait them to answer.
Yeah.
أي سؤال?
All right. So I think there is a chat here. Let me know. So 3 minus 3 equals 1. What did I say? Did I say something else?
لا, no thanks. In Arabic, no thanks. It's me.
All right. Okay. So I will see you after 20 minutes, right?
No. Yes. After 20 minutes, بعد 20 دقيقة إن شاء الله نلتقي بعد الاستراحة. Thank you, Doctor.
Thank you. I'll see you in 20 minutes. Bye.
Bye. مدة الاستراحة 20 دقيقة إن شاء الله. السلام عليكم. السلام عليكم ورحمة الله وبركاته. نعود من جديد إلى دورة هندسة ريمان. Welcome back, دكتور إليانا.
Thank you. So should I start or wait one more minute?
No.
Yeah.
Yes.
I'll start. Yeah, okay, very well. So before moving on to a new part, which is about vector fields, flows, and I would like to look at this theorem, well, 7 in my files, because it's related to what we've seen before. Now, this is that because I would like to take an application to see that, you see, all this sophisticated language is actually an extension of what we say. I mean, we are extending things that we already know, parallel geometry from coordinate geometry, and we generalize this and we change the language into a language of manifolds. Anyway, so suppose that f is a smooth map from a manifold to another one. Suppose that n is greater than or equal to n, and so the dimension of the domain greater than or equal to the dimension of the codomain, and then we take a regular value for the function. Now we know already from what you've seen previously that this f inverse of y, the pre-image of y, being non-zero, will be a submanifold on M, so manifold itself. Now we take a point x on this submanifold, and then the tangent space at x to f inverse of y, so to the submanifold, is in fact the kernel. Well, the tangent is the same as the differential. It's another notation for the differential. So it's the kernel of the differential of f. So I'm going to take an example here, and we are going to see how we can find the tangent space at a point to a sphere, for instance. All right. So something that I'm pretty sure you know and you will recognize when you see. So let me write here the theorem shortly. So this is the following. We have a function going from a manifold to another manifold, n, right? Smooth, again, smooth. We want m greater than or equal to n. We want y to be a regular value for our function f, and such that f inverse of y is not empty. So again, this means, using what we've seen previously, that f inverse of y is a m minus n dimensional submanifold of the manifold M. Okay, so a manifold itself with dimension m minus n, then the theorem claims that the tangent space at a point x to f inverse, so x is a point of f inverse of y, of course, it's a point on this manifold. So the tangent space at x to this f inverse of y is the kernel of the differential of f at the point x. Okay, so that's pretty nice. And let's take as an application, let's take the function f defined on R n plus 1 with values in R, given by f of x equals the norm of x squared. So this means f of x1 up to xn plus 1 equals to x1 squared plus x2 squared plus xn plus 1 squared. Okay, now we did this for n equals 2 for 3 components x, y, z, if you remember 1 hour ago. So the rank, so what is the rank of f? So what is, let me do it like this, what is f inverse of 1? This contains all the points in Rn plus 1 for which f of x is 1, so for which the norm of x squared is 1, and this is simply the n-dimensional sphere, right? We did show that 1 is a regular value. We take it for the case of 3 coordinates, but it's the same thing when you compute the rank of f. You look at the rank of the Jacobi matrix. The Jacobi matrix is a row matrix in which the entries are 2x1, 2x2 up to 2xn plus 1. We want the rank to be strictly less than the minimum between n minus n plus 1 and 1. So the rank to be 0. So the only critical value will be 0, 0, 0. So f of 0, which is 0, is the only critical value. So the only critical point is 0, 0, 0. The origin, the only critical value is 0, which means that 1 is a regular value. It's pretty of f for f. It's pretty clear that f inverse of 1 is not empty. Right, you take the point 1, 0, 0, 0, which belongs there, which means that this is an n-dimensional submanifold. So we know already, but what we want to do is to determine the equation of the tangent space at a point to the sphere. Okay, so we have the sphere. So we want to take a point on the sphere and to write down to find the equation of the tangent space at this point, right? So let's take a point here, x on the sphere, and well, our this theorem says that the tangent. So this is Sn. This is 1. Sn. So the tangent at the point x here to the sphere is what? Is the kernel of the differential of f at the point x, right? This is what the theorem says. So what is the kernel? The kernel of the differential will contain all the vectors v of Rn plus 1, for which the differential of f at x calculated at the vector v is equal to 0, right? This is the kernel of a map. So I'm going to say f v1 vn plus 1 points of Rn plus 1 n plus 1 with the property. How do I write this? This is the matrix of the differential, which is the matrix of the differential, that's the Jacobi matrix, times, well, transpose, so we get it properly, times v, times the vector v is equal to 0. So this will contain all the points v1 up to vn plus 1 of Rn plus 1. Okay, well, I'm writing it as a row, so I will have something like this. That's 2x1, 2x2, up to 2xn times, I'm identifying xn plus 1 components, v1, v2, vn plus 1, right? So this was transposed, equals 0. So this will contain all vectors v1 up to vn plus 1 in Rn plus 1, for which 2x1 v1 plus 2x2 v2, I'm dividing by 2 directly, so it's x1 v1 plus x2 v2 plus xn plus 1 vn plus 1. Well, I write the indices up here. 2 n plus 1 is equal to 0. Okay, something like this. So maybe you know that when you have a point on the sphere, then the equation of the tangent plane is indeed of this form, right? So that's a nice way to find, you know, the equations for the tangent spaces to a manifold by identifying this manifold as a submanifold on a larger space, and then applying this result. Any questions? All right, very well. So then we move on, and we are going to start talking about vector fields, and then about flows. So let's see what a vector field. Do you remember what the tangent bundle is, right? I did remind you at the beginning of the lecture today. The tangent bundle is given by this Tm, which is the union, this joint union of all tangent spaces at every point, at all points of a manifold, and then we take the projection maps, right? Taking a tangent vector at P to the manifold M into P, into the origin, and then a section of the tangent bundle is called a vector field on the manifold. Now, the section simply means that you define the map from M to Tm right, such that you have a commutative diagram here. So you simply take every point P of M into a tangent vector at the point P to the manifold M, right? So something like that, something like this is called a vector field or smooth vector field, and we denote by this chi of M the set of all. The space of all smooth vector fields. This gamma of T of M, this means the set of sections. It comes from the general theory of the fiber bundle. So I didn't talk here. I didn't go on the general case. We just talked about the tangent bundle. So again, what is M is a manifold. M is a manifold. We take T of M, right? The tangent bundle, something like this. Remember this, everything here, every tangent vector goes into P, into its origin through the map, and then a section of the tangent bundle means a map defined from M into T of M, which takes a point P here into a vector which is tangent at the point P to the M for every P of M. Something like this is called a vector field. A vector field on the manifold M, okay? So section of the tangent bundle. So again, this is the notation for all the tangent, for all the smooth vector fields on a manifold. All right, and now here, when we have a chart on M, then this chart will induce the so-called canonical frame on the tangent bundle over U, which is denoted by something like this. Now I'm going to try to remind you what is this and to make you understand what we mean here. So again, we start with the, what we would like to do, what we are trying to do here, is to find some sort of a basis for this space, right? So we'd like to write any vector field as a linear combination of some elements from some sort of a basis there, right? So we can do that. We can work with in an algebraic way here. Now remember what we did when we were talking about the tangent. The tangent bundle here. The tangent bundle was defined as the union of the tangent space. So when you have at any point, so when you have a manifold M, right? Then suppose that you take a chart on M. Okay, this chart will induce some basis, right? A basis on the tangent. So this is about P, about some point P of M. So we'll get a basis here on the tangent space at the point P at Q, which is the same as the tangent space at the point P of M. So this is M, P is a point here. You take an open neighborhood, right? The tangent space at P at the point P to U is the same as the one at the point P to M, to the manifold M. So we take a chart here. So this chart will determine a basis, if you remember, a basis for TPU or for TPM, a local basis, a mobile basis, right? It depends on the chart. So remember, we were denoting this elements of the basis by something like that, right? We talked even today a little bit at the beginning. And now so you see, for every P, you take a chart and you get something like this, which means that you can look at this guys here, right? They still depend on the chart as functions from U into the vector bundle of U, right? And every point P of U will go into what we know already what it is, right? This at the point P. Remember, this is simply the differential of the homeomorphism of the chart inverse, right? Applied on the standard vectors, the standard vector from the basis of Rn, right? So we can see this as a map like this, right? So we are going to say that these functions, right? They are functions. So they are functions going from U into T of U. So they are functions of this type, you see. So they all will be here, right? sections of this tangent bundle of U. So they will be vector fields. They will be vector fields on U. Now we say that this is a frame. Okay, so we are going to write every vector field as a linear combination of these vector fields, right? So they come as functions defined, something like this, where we use vectors that were bases for the tangent space at the point P to the manifold. To the manifold U, to the open set U. So this means that if X is a vector field on M, then we can write it as a linear combination of those vector fields. So it's something like that. Xi, partial over partial, X, this very weird notation, I agree with you, I running from 1 to M. And so these X's are smooth functions defined on U, right? So this frame is like a basis for the space of the vector fields over U. Okay, and now so once we have this, right, we can express every vector field as a linear combination of this. Now there is another way to think of vector fields. Right, so the first way, there is a dual way to look at the vector fields. The first one is a vector field is the section of the tangent bundle. So it's a map defined like this. All right, that's pretty clear. And now let's look at vector fields as so-called derivations. So I'm going to write like this. So vector fields as derivations. Okay, so let me show you here, and then I'm going to come back to, all right, so this is what you've just seen. Yeah, maybe we should, yeah, we are going to take that example afterwards. So you see, we are going to define the derivative along a vector field to be something like this, right? So x of f is a map defined from M into R in which P goes into xp of f. Remember that xp is a tangent vector at P to the manifold M. So it applies on smooth functions defined on M, on elements of this C infinite of M, right? So let me go back to and write it here. I think it's easier to understand. So suppose that you have X, you see, a vector field like this, and then we say that we define x of f, right? So f is a smooth function defined on M. So this means smooth from M to R, smooth functions from M to R. So we define this like this, right? The point P goes into xp applied on f. Remember, xp is a tangent vector, so it defined like this. Tangent vector at P to the manifold M, and this is called the derivative along the vector field x of the smooth function f. Okay, of the smooth function f. Now, it can be checked, seen that this is indeed smooth and everything. Let me show you how we compute that this derivative, right? So I'm going to take a simple example. Suppose that x is simply of the form x d partial over partial x plus y partial over partial y. So that's, you see, these are the elements of the basis, so-called frame, right? On the space of the vector fields, right? And then let's take a function. So I'm going to take f of x, y, and z to be, let's say, x squared plus y squared plus z squared, right? So we have a function and the vector field. The components of this vector field are x and y, right? So those partial over partial x, partial over partial y are just the elements of the basis, the frame. Then what will be x of f? What is f of x? What's the derivative of this function along this vector field? Well, this will be x partial f over partial x plus y partial f over partial y. So you simply, you see, x of f, so you put an f and you apply it here, right? So you would simply calculate partial derivatives of f, right, here with respect to x and y. So this is what? This is x times 2x, right, plus y times 2y. So this is 2x squared plus 2y squared, right? So I think that's clear how we compute the derivative of a function along a vector field. And now we are ready to go and define the derivation of the real algebra. Yeah, so the derivation of the real algebra of real valued functions defined on the manifold M to be a linear map, right, going from this C infinite of M, these are the smooth functions M to R, into C infinite M, which are, so linear, right, additive and homogeneous, which satisfy again this Leibniz rule. You see, the derivation applied D of Fg is F D of G plus D of F and G, right? Again, this should say look familiar. And now what we want to do here is to identify a vector field with a derivation of this algebra of smooth functions. So this is what we are going to do right now. So again, what is a vector field? It's simply a vector field. We define it to be a section of the tangent bundle. Right, so it's some map taking a point P into a tangent vector at P to the manifold M. Then, so this is a tangent vector, this is a vector field. Then a derivation, so derivation of the algebra of functions, real functions defined on M, smooth functions, is some map going from the functions into the functions, which is linear and such that what you get is f times d of g, Leibniz rule, plus d of f times g for every functions f and g, smooth functions defined on M. So we would like, as I said, to identify the vector fields with derivations of this algebra. You see, a dual way to see vector fields. So what we are doing is the following. We are going to take the following map from C infinite of M to C infinite of M. So x is our vector field. So we take f into x of f, right? So f, remember, f is a function from M to R. So f of x of f must lie here, right? So it must be a function from M to R. So we apply it on some point P of M, and we define it to be xp, this is a tangent vector at P to the manifold M, applied on F. Remember that xp is a tangent vector, so this I wrote it somewhere. Yeah, so it runs, you know, the domain for xp is the set of the algebra of smooth functions, real functions defined on M, right? So at least at the level of definition, this is correctly defined. Now it's we can prove that this map is linear and this map is a derivation. So we can prove that this map defined like this is indeed a derivation of the algebra of smooth functions defined on M, right? And then so this can be done. That's a simple computation. And then so you see we went from a vector from a vector field, right? From a vector field, and via the vector field we defined the derivation of the algebra of functions. Now let's look at the other way around. So suppose that D is a derivation of this algebra, right? Or a derivation. And we want to define a vector field, right? To make this kind of, way to see a vector field through via a derivation. So we define the following vector field from M into T of M, and then P must be, you see, must go into a vector which is tangent at the point P to the manifold M. So we define it like this. XP, so being here, acts on some function f, and we define it to be df of P. Okay, so if you look at how we define d of f lies here, so f lies here, d of f lies here, so it's indeed a function from n to r, so it makes sense to talk about df of P. Now, it happens that these are correctly defined, and it happens that we can, using this, what is it? Using these identifications, okay, so this is what I wrote there. Using this identification, we can look at the vector field in a dual way, either as a section of the tangent bundle, or as a derivation of the real algebra of smooth real valued functions defined on M, right? So it depends on what we need. We are going to pretty often look at this at vector fields as derivations, right? It's easier to work. It's more intuitive to work with this kind of functions. All right. Now here you have results saying that everything is correctly defined and so on. So I'm going to skip this part, and I'm going to move on to see what the local flows are. Okay, so all right, let's see. Map is called a local flow on a manifold if these conditions hold. And now let me write it on a white paper. So the domain on which we define this map phi must look like this. You see, so I try to sketch it here to try to represent it. So it's a subset of R times M, which contains 0 times M, right? So every time you cut this by R times X, you get an interval times X, right? And that interval must be it's an open interval which contains 0. That's an interval of R, right? So if you represent R as a horizontal line and M, the manifold M, as a vertical axis, then A looks a little bit like that. So anyway, suppose that we have a good set on which we define a local flow. So if something like this happens, these two conditions hold, then well, we have a local flow. So let me take a white page here. Right. Oh, sorry. Oh no. All right. I'm not going back to. What's wrong? Yeah. What's wrong? Okay. Very well. So, yeah, so we say that phi defined on A, so again, A looks like that, right? Where we identify this is R and this is the manifold. So this is a subset of R times the manifold. M is a manifold, n-dimensional manifold, and with values in M. So we say that phi is a local flow on the manifold M if two conditions hold. First is that phi evaluated at 0 and x is x for every x of M. You see the domain looks like this, so it's a subset of Rm, so I have two components there. And second is that phi of S and phi of T of X. So phi of T of X is phi applied on a point here, so the image will be in M, so this is in M, so it's fine, right? This is in R and this is in M. So this is phi of S plus T and X for every X in M, and for every S and T real numbers for which this makes sense, right? Depending on how the set A is here. All right, and now let's look first, let's just take a simple example here, and let's show that. I'm going to take an example before going further, and we are going to take the map gamma from R times R4 into R is n into Rn, and let's prove that. So this is R, define like this: gamma of t, and a point here in Rn will be something of the form x1 up to xn, and we define it. So this is how we define it: exponential of t x1. I don't know what happens here. So this is t and x1 xn. So exponential of tx1 up to exponential of txn. Okay, and we want to show that this is a flow on Rn. It will be, it's more than a local flow. We call this a general flow. You see, local when this A is strictly contained into R times M, right? So now here we take the A. Okay, so that's very weird. Keeps moving. All right. So we want to show that this is a local flow. So let's go and check these two conditions. So first, let's see what is gamma of 0 and x, right? I'm checking this condition. So this is gamma of 0 and x will be of the form x1 up to xn, right? Then I'm replacing in the definition, I'm using the definition of the function. This is exponential of 0 x1 up to exponential of 0 xn. Exponential of 0, that's 1. So this will be x1, xn. So this is indeed our x. And then for the second condition, let's go and check what is phi of s and phi of t of x. So this is phi of s, and now phi of t of x will be, it has this form, right? So this is exponential of tx1 up to exponential of txn, right? So this will be equal to, now this is my new x1, right, up to xn. So again, I'm replacing in the definition of the, well, it's not phi, it's gamma, right, gamma. So it's exponential of s times x1, which is exponential of tx1, up to exponential of s times exponential of txn. This is exponential of s plus t x1 up to exponential of x plus t xn, and this is precisely gamma of s plus t and x1 xn, which is x, right? So this is the second part of the on the second conditions there, right? So we know now what a local flow is, or a global flow, when it's defined on the whole set, when it can be defined on the whole set. And then we are going to define the map, something like this: alpha x running from Ix. Now Ix is simply, you see, when you have this is your A, this is the set A. Ix is the intersection between A and X, right? So it's this kind of interval, something like that. This is an Ix for this X of M. For this X of M, this will be Ix, and so on, right? So this is a subset. This is a subset of, I don't know what's happening here. A subset of where is, yes, of M. So we define it. We define the map like this through alpha x of t equals the flow of t and x, and this is called the integral curve. The integral curve through x. The integral curve through x. Now, what we are going to see, in what follows, we'll see that every local flow. Okay, so this is what we've just talked about. We're going to see that every local flow induces a vector field, and the other way around, every vector field on a manifold has a maximal local flow, right, which can be computed by putting together the maximal integral curves. I'm going to take examples. This is the easiest way to understand. So again, every local flow induces a vector field, and every vector field has a maximal local flow, right? So this is what I'm writing here. Okay, this is the example that we just took. So here I'm giving some definitions that I'm going to explain, right, in 1 second, and then we are going to take some examples to find the integral curves for the vector field, the maximum curves, and then so on. A complete vector field simply is a vector field for which the local flow is global, right? The one that you've seen previously, right? So which can be defined not only on the subset there, but on the whole R times the manifold. Anyway, we'll see. So before this, let me write that's kind of important. So it's, you know, the way that we are dealing with the practical examples. Okay, what's happening there? All right. So every local flow, so if phi is a local flow, then phi will induce a vector field. So the vector field is defined like this. So you see, again, it's a section of the tangent bundle. So we need to see what is, so every x here in M goes into a tangent vector at x to the manifold, and this is defined to be the derivative of alpha x is tangent at x. And then, so this is 1, and on the other way around, every vector field, so if this is a vector field on M, every vector field has a maximal local flow phi defined on A in M, which can be found like that. We compute, so which can be found by computing for every x in N, the maximum integral curve, so what we define here, the maximal means defined on the maximal interval. There is such something like that. It can be proved. The max. Right. Sorry. So this is alpha x. That derivative of alpha x. Oh, it's t. Sorry, is the tangent vector at alpha x of t here, and then alpha x 0. See, this is a initial value problem, right? First equation is equal to x, and then we simply take the flux, the flow to be by definition alpha x of t, or something like that, right? So let me look at these examples here. So what I wrote here is what I'm explaining on this part here, right? I'm defining the derivative, but you will see in example, this is the easiest way. So let's start with the first one and find some integral curves, okay? So we take some examples here. So I'm going to a white page. So first example here, let's say find the integral curves of the vector field defined like that, x to some point xy. So we define the vector field by defining any tangent vector, right? So this will be x, going to go like that, partial x, remember the base, the frame, minus y partial over partial y. Okay, this is a section here. Okay. All right, so it's a vector field over R squared. So let's find the integral curves. All right, so what are the integral curves? Well, they are curves, so it's something like that. So we define them on some interval, right? We'll see what is this maximal interval into the manifold, which is R squared here. We are on R squared. This is our manifold. So this means what? This means that the gamma will have gamma of t. So maybe let's gamma runs from an interval into R squared. So gamma of t will be something here, right? So it will have two components, x of t and y of t. Okay, now we want to do what? To find the integral curves. What are the integral curves? They are defined by something like this, right? So the derivative of gamma, well, I'm calling alpha gamma. So we have that. What is the derivative of gamma with respect to t? That gamma dot, right? Denoted there by gamma dot. Well, we'll have the first component is x dot. This is the derivative, right? Partial over partial x plus gamma dot y dot partial over partial y, and this must be equal to what? So this is this guy here is the same. It's another notation. Is the same thing. So x at alpha of t. So this must be the same as x at x and y, right? Which is what? Which is x partial over partial x minus y partial over partial y, which means that this guy must be x and this guy must be negative y, right? So I'm saying x dot, this is like x prime. It's a little bit weird with this notation, so because we can have more than one variable anyway, so it's minus y, right? So I want to, solve this thing. There's a system of differential equation, right? So we have what? I'm going to replace it's x dot over x. This is 1, right? So you integrate, so it's like integral of 1 over x, right? Dx over x. This is integral of 1 ut. So we have what? We have logarithm of x equals, well, we have an absolute value. I'm going to ignore all these details. I'm going to, right? This is t plus a constant. And then this means what? That x is exponential of t plus c, right? Which means exponential of t times exponential of c, which is some constant c1, right? And similarly, so we'll have what? We'll have that x of t is some constant exponential of t, and similarly y of t, because of the minus, we'll get an exponential of negative t, something like that, right? So what is our integral curve? Gamma of t. So the integral curve will be gamma of t given by x of t and y of t, right? So will be c1 exponential of t, c2 exponential of negative t. You see, t can be any real number, so that's a global. We can define these curves on the whole number line, right? So this is how we find the integral curves. Again, let's find the maximal integral curve starting at a point. So this means starting at a point means that gamma at 0 is AB, right? So when we write gamma of 0, okay, if gamma is an integral curve, and we write gamma of 0 equals P, then we say that the curve starts at P. Remember that 0 must always be there in the interval, right? So let's take this example also. Find the maximal integral curve gamma of t starting at AB of the vector field. Okay, so I forgot the expression of the vector, so it's partial partial x plus x, all right. So this is x equals partial over partial x, so the first component is 1 plus x partial over partial y, again a vector field on R squared, right? So we do what? We look for gamma of t, which is of the form x of t, y of t, because it's on R squared, so two components with the property that gamma of 0 equals AB, starting at the point AB, right? Now, what is gamma dot? I'm going to denote it like this, so you get used with all notations there. So gamma dot of t, this is simply x dot, y dot, okay? So this is the same as writing it as x dot partial over partial x, right? An alternative way to write as a vector with components or as a linear combination of the elements from the basis. Okay, and this has to be x, so this has to be this one, partial over partial x plus x partial over partial y. Okay, so let's see what we get. We get x dot equals 1. We get y dot equals x. Okay, and we have the initial conditions that x of 0, so gamma of a0 is ab, x of 0 is a, and y of 0 is b, right? Initial conditions. So if x dot is 1, then x of t, we integrate, so that's x plus c, right? If y dot is x, which is, this is t, huh? T plus c, right? We integrate with respect to t on the other side, so y dot is x, which is t plus c. You integrate integral t, that's t squared over 2, integral of c, that's ct plus some d, right? And then x of 0 is what? Is c, it must be a, and y of 0, this is d, and this must be b, right? So what is the curve? The integral curve is given by gamma of t, so x is t plus a, y is t squared over 2 plus c was a, yes, t plus d was b, something like that. Okay, so you see, I have r over the whole r, which means that the maximal integral curve can be defined on the whole r, right? So we go from r into r squared. Okay, so that's another example here. Let me see what other examples do we have here. All right, let's look at example 3 also. So we see that not all integral curves are defined on the whole R, on the whole set of real numbers. All right, so let's also look at this one. This example. Okay, so let's take the vector. Let's take the vector field x given by x squared. It was x squared partial over partial x. So a vector field over R. Okay, something like that. So we want the maximal curve, find the maximal integral curve of x starting at x equals 2. Okay, so again, we want so that gamma, right, will simply be some x of t, right, over R. So we have what? We have that gamma dot must be x, right? So gamma dot means x dot, right, of t equals x squared, right? Looking here, so it's x squared together with the initial condition x of 0 equals 2. Okay, so let's see what we get here. We have x dot, looking here, over x squared, that is equal to 1. So you integrate, so that's integral dx over x squared is integral of 1 dt, right? So this is negative 1 over x, and this is t plus c. So we have what? 1 over x is minus t plus c, right? So x will be, x of t will be minus 1 over t plus c, something like that, right? Now we have x of 0 and one second, all right? So x of 0, this moves all the time, x of 0 equals 2, which means that negative 1 over 2 plus c, 0 plus c, right, equals 2. So c will be negative 1 over 2. So what is our gamma of t? Is x of t, which is negative 1 over t plus c, which means t minus 1 over 2. Okay, so you see, this function, this must be continuous, so t cannot be 1 over 2, right? T cannot be 1 over 2. So the interval, the maximal interval on which we take this solution is either, if you know a little bit of differential equation, so it's either negative infinity 1 over 2 or 1 over 2 infinite, right? Now, which one do we take? We necessarily, if you remember, we necessarily need 0 to belong to the domain, right? I wrote it somewhere, right? Maybe we can see it here. 0 must belong to the domain necessarily. So I'm taking that interval containing 0. So in our case, the maximal interval is negative infinite 1 over 2. That's the maximal integral on which this is defined. Okay, so let me see what we have here. All right. All right, now for the next one, try to do it yourself. It's like the same thing, right? With n components, you need to show that this is not complete. So complete vector field is a vector field for which the local flow is global. So we can define it over the whole R, right? So for instance, our last example was not global flow because you cannot define over the whole R, right? But the previous one, yes. All right, so this is how we find integral curves. And then let's see what's next. Right, so we talked about this, right? I'm going to skip it. Okay. All right, this is another example. Very well. Now, as I said, a vector field is called complete if the integral curves are defined all the time. So if the domain for every gamma that you've seen on the previous example is the whole R times n. And now, what is this phi t? So I'm defining it here. Sorry, here we are. So you see, this phi t, right, is defined on the domain of the you see these pairs of the form TP. You can see here the domain TP with where P runs over the manifold M, and T is on that interval where we can define the curves, right? So it's a subset of R times M, and we define it such that every point P, right, goes into this phi phi t, which is gamma phi. These are the integral curves, right? So in fact, we can work with this flow phi tx. Think of this as the flow, indeed, as the position of on the integral curves at the moment t. Okay, this is how you need to interpret this. So when you, I think I have a picture maybe somewhere. I drew it. Didn't. Maybe I did. Yes, you see here. So you have a relation, right? So phi x of t means that you are at the moment t on this integral curve. So what we are seeing here is that so let me write this maybe on the, let's see if I can write. So I'm looking here, all right, here. Okay, we can see this. Well, all right. So you see, phi xt means that you are at moment t. So it's like after s things seconds or something. At the moment s, you are at phi s, which is here, you see, and then you move another t, right? So you go from p s, let's say it's s seconds until you reach here, and then you go another t seconds, right? So it's like going from the origin to s plus t seconds. This is what we are writing here. Okay, so something like this. Something like this will be a diffeomorphism. Remember what diffeomorphism is? That's bijection, smooth, with the inverse also smooth. And then the inverse, right, will be this phi x at time negative t, right? So there's this geometric way to see this. Now, maybe I should take this example because it talks about. Yes, I will take it. Just give me a second. It talks about this way of moving on the curves, on the integral curves, or for a flow. And then you have something like this. You have that when it's what we showed on the picture, is that phi s composite phi t is in fact phi s plus t, which means that we can find a group homomorphism, right? A homomorphism of groups between the additive group of the real numbers, it's some algebra here, into the group of diffeomorphisms of a manifold. So this means bijective, smooth and inverse smooth from M to M, from the manifold to the manifold itself. And then T runs into this diffeomorphism, right? So we can, I'm getting rid of this. We can have we have this diffeomorphism, and this is called a one-parameter group of diffeomorphisms, right? So this relation here, okay, page up, not working. Come on. So this relation is precisely why we have a different. You see, s plus t. This will take us into the additive group R, and well, the composite here. The composite here, right, tells us that here we have the composite of the composite for the operation. Let me take this example that I was talking about. It's still about integral curves, but it's a nice geometric way, and to see what we explained here with this one parameter group. So suppose that you have x of the form negative y partial over partial x plus x partial over partial y, and we want to, so this is a field over r squared, and we want to find the integral curves, okay, for the integral curves. So let's call them gamma of t. So they are in r squared. We'll have two components here, x of t and y of t. So we have what? We have gamma dot. This is x dot, whatever, y dot. And this has to be the same as x. So the components negative y and x. So we have x prime, x dot is negative y, and y dot is x. Okay. So if you draw it, you will have something of the form. I'm going to take this y, right, and put it here. So I have x equals to negative x second, right? Something like that, which means x second plus x equals 0, right? So characteristic equation, right? R squared plus 1 equals 0. R is plus or minus y. So you will have that x of t will be what? Will be some a cosine of theta minus b sine of theta, something like this, and y of t will be a sine of theta plus b cosine of theta. Okay, All right, so so your gamma of t, the integral curve, will be a cosine of theta minus b sine of theta, a sine of theta plus b cosine of theta. Well, this is what, if you think of these equations, this is a circle which goes counterclockwise. Okay, so if we want to draw it, say this is a system of coordinates. If you want to draw this curve and the flow, the associated flow, then right, you will have so like that, something like that. Okay, so say this is a circle, and then the next one will come here, the next tangent vector, and the tangent vector to see the, you know, the tangent, the vector field, the tangent field, the vector field. Okay, something like that. Right? So we move counterclockwise on this surface, right? Then if you go here, you will do the same thing, right? You will have a vector horizontal, and then you will come and down. If you draw them, if you give values to t, you will see that they look like this. Okay, something like this. So if we want to start at every, so for each we have a unique integral curve, starting at AB points in R squared. All right, so something like that. All right, so let's see. Okay, we talked about this. I'm going to skip the complete vector fields, and then we are going to talk a little bit. We move on to the practically last part of our course. Well, that's a long part, so I'm happy that I can have like 10-15 minutes today, maybe a little bit more, to talk about this extreme algebra. All right, so in fact, the goal, for this last part, our goal is to integrate on manifolds. So let me see if I have a content here. Yes. So you see, what we want is to reach this Stokes theorem. This will happen tomorrow, of course. To reach this Stokes theorem, which allows us to integrate on manifolds. Now, you see, the theorem looks like this: integral over m d omega equals integral on the boundary of m omega. So we don't really know what this means, but maybe, so we are going to explain everything, but maybe it's better than today I'm taking care of the cotangent bundle and manifolds with boundary. Let me start with manifolds with boundary. We need them again when we talk about Stokes theorem. We have here this nabla m. This means the boundary of the manifold, but we didn't say anything until now about something like that, about boundary on manifolds. So what is this? You see, the idea is the following. When we talk about manifolds, as hopefully you remember, we model them, we ask them to be locally Euclidean. So this means that around every point on the manifold, you can find an open neighborhood which is homeomorphic. So it's locally the manifold is locally homeomorphic with an open subset of Rn. So of a Euclidean space. So open, you see, open. Now, what is a manifold with a boundary? Think for instance that instead of, so I'm going to go back here, think that instead of working, so let me explain you here like this maybe. So, right, so what was a manifold? You have your space, and for every point here on the manifold, you can find an open set which is homeomorphic with an open set of phi of u, which is an open set of R, let's say n, right? Dimension of n. What if instead of taking open subsets of Rm, we work with open subsets of Hm? Hm is half space, right? So it's like, for instance, if you think of R squared, right? This is the whole plane, that H squared will be only, only half of, oh, sorry, I'm talking about R. That's not good. So H squared will be only, let's say half the upper plane, half plane. So if you think of R cube, right? You have a system of coordinates like that. This is R cube. Now H cube will be, for instance, you cut your space into two and you only take the upper half space or the lower one, it doesn't matter which, right? So what if instead of modeling everything on Rm, we model on Hn? Now, you see, this Hn has a boundary, right? So this inequality that you see here, it's not, this inequality that you see here, it's not strict, right? You have greater than equal. So this has a boundary that it's defined here. Now the notions are the classical notions in the topology. We can define the boundary. We can define the interior, right? Of Hn. So instead of what I'm saying here is that instead of instead of working with Rm, we work with Hn. What we obtain is the so-called manifolds with boundary. And now, okay, how do I get rid of this? Just 1 second. Yeah, all right, very well. Okay. So you see here we define the boundary here, and we define the interior of Hn. But I guess you pretty much know what this is. Now, in a similar way as we are doing it for the manifold, the classical manifolds without boundary, we can define an atlas, right? But again, so we just define it in the same way. The domains of the charts must cover their union must be n, must cover n, and then the homeomorphisms are taking open sets of m into open sets of Hm, or of this half space, right? And then the charts must be, we say, Hn compatible. This simply meaning that you have the same kind of transition map here, phi alpha times phi beta inverse, and we want it to be smooth, right? We can have some sort of a boundary there, right? But we know how to deal with this. So something like this is called a smooth n-dimensional manifold with boundary. This is just because we need something like this when we talk about integration on manifolds. I think I put some examples here. So I'm defining here the boundary, right, and the interior. And well, every manifold with boundary can be partitioned into two subsets: its interior and its boundary. The interior is open, the boundary is closed, right? So here we define the same kind of differentiable structure. And yes, I do have some examples here. You see, for instance, the closed interval, right, left and right, closed interval 0, 1. This is a manifold with boundary. What is the interior? So the first one there. What is the interior? It's the open interval 0, 1, right? What will be the boundary? Well, the boundary will be given by, we have 2 points, 0 and 1. On the second interval, right, interior is open interval 0, 1. Boundary is 0. Right, now the last one is either a manifold. You see, this is an open interval, so it's an open subset of R. It's a manifold. We can see it as a manifold without boundary, right? As a manifold like the ones that we were talking now. We can also say it's a manifold with boundary 0. Now the closed ball in Rn, this is a manifold with boundary. What's the interior? Is the open ball. What is the boundary? It's simply the n-1 dimensional sphere. Think of, for instance, think of R squared, right? Then you take a disk, the closed disk, right? So the interior is the open disk, and then the boundary is the circle, right? So that's it's like the 2 minus 1 one-dimensional sphere, the circle. All right, so these are the manifolds with boundary. Now everything else is constructed in the similar way. We can define a smooth map again via charts. So we always take the local representation. There are some details here to be dealt with, but there is nothing that doesn't work. So everything that we talked about before still happen here. Now we don't know yet what is the cotangent boundary or the exterior powers, but everything else, you know, sorry, I'm not, well, I'm going back here. Everything else can be defined similarly. Now, what happens is that when we have manifolds with boundary, we can orient the manifolds. Now, this is a very long talk about the orientation on manifolds. There are different ways to orient the manifolds. I won't insist here because we would need a semester class to really explain in details the orientation of on manifolds, but think of this as something something in the let me explain in the following way. So think, for instance, at a sphere. Okay, think, for instance, at a sphere. So we already met this notion of an orientable manifold. At the very beginning of our class, I said that a manifold is orientable if the determinant of that matrix obtained from charts, if you remember, is greater than 0. So we did talk a little bit about orientable. You didn't insist. Think of a sphere, for instance. I'm going to just try to make you understand what is this. Think of a sphere. Think that on this sphere, okay, think that on this sphere, you take somewhere a point, right? And then you take the tangent space here, and then you take a normal vector, right? A normal vector like that. I'm going to call it A. And then imagine that you move, you see, you move on the sphere, you move, right? On the sphere like that, and you move your point, so every time you bring with you the tangent space together with the normal, right? And you keep moving. You imagine that you have a curve, for instance, on the sphere, and you keep moving, right? This normal vector will move accordingly, but if you go back continuously at your original point, when you reach here, the normal vector will be on the same position, right? It doesn't move inward, it stays erected. Okay, so sphere is orientable. It's just, you know, that's a very vague thing. It's just for you to understand a little bit what we mean. Now, an example of a space which is not orientable is, for instance, the so-called Möbius band, Möbius strip. Möbius strip. Okay, so this is a non-orientable. A Möbius strip, imagine that you take I'm trying to draw it, I'm not very good in drawing this. So you take a piece of paper, a strip of paper like that, and then you stick this as they are, these two corners, and these two you flip them, right? So A, B, C, D. So A, B stay where they are, like that, and then you flip C and D. C and D, right? So here you will have something like that, and then you join C with A, right, and D with B. So you'll have something like that. Okay. Okay, so you flip it once, and then you do this with them. Well, it's not very, right? You can try to do it with a piece of paper, right? You take a strip of paper, you flip one side, and then you glue the new opposite, corresponding sides there. This is non-orientable. If you think of this, so we do the same thing as we've done with the sphere. Imagine that you take a point, you take the tangent, plane here, and then you take the normal vector, and then you move. What happens is that when you move here on this Möbius strip, when you reach with your point this position, your normal will be inward, right? This is a strip. This is a shape having one single face, if you want, right? So this is a non-orientable manifold. Now, what happens is that so there are manifolds which are orientable, and there are manifolds which are not non-orientable. We are going to see that this orientability issue is strictly related to what we call forms. N forms on a manifold that we are going to define tomorrow, and to integration on manifolds. So anyway, bottom line is that every connected orientable manifold has exactly two orientation, right? So one is given by determinant positive, for instance, and the other one is given by determinant negative. So there are ways to understand a little bit better this orientable, non-orientable thing, but of course, the Euclidean space is orientable, right? Spheres are orientable, and so on. We are going to see a little bit, maybe tomorrow or a little bit more, that every orientable manifold with boundary admits an orientation which is induced on the boundary, which is defined somehow. So, for instance, if you have a ball, right? So a ball, this means a sphere which is, filled by that. Then you can orient this ball, and the orientation on the ball will give an orientation on the boundary, which is a sphere, right? And they are compatible, right? So we can work with them. Okay, we'll see a little bit tomorrow about. But anyway, we won't go into details about the orientation. But I need few notions to be able to integrate on manifolds, right? So just remember that there are manifolds which are orientable, for instance, a sphere or Euclidean spaces. And then if the manifold has boundary, it's a manifold with boundary, then the orientation induce an orientation on the boundary which is compatible with the orientation on the manifold. Okay. Questions?
هل توجد أسئلة؟ أي أسئلة؟ They said
No?
أيوة, no, they said no.
All right.
بس
Okay, yes?
they want the name of the book so they can use it for study.
Send them. I will send them. I made some slides. I used a lot of books, so I can send them a bibliography, and I will send the slides that I made.
Okay, doctor.
Okay. All right. Okay.
Thank you.
All
Thank
right. Thank you. I'll see you tomorrow.
you. Complete بإذن الله. Thank you.
Bye.
Thank you very much.
I'll see you tomorrow. Thanks.
إن شاء الله. Thank you. موعدنا غدا إن شاء الله اليوم الثالث من دورة هندسة ريمان. يعطيكم العافية. سبحانك اللهم بحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك. بأمان الله.